Hello, this is Nick, and I'll be working on a series of videos about reading graphs in the physical sciences. Right, reading graph in physical science. The simple graphs are pretty easy to read, but sometimes the graphs could become quite complicated. So I've structured this into a series of videos, and this is going to be part one of section A. Part one is going to talk about distance, velocity, acceleration, and all of those versus time. Right? In other words, distance and time, velocity and time, and acceleration and time. Um, part two will deal with other types of graphs, such as force and so on. So this particular part one is dealing mainly with distance, velocity, and acceleration, all of them in association with time. Let me get this a little bigger so we can. All right. Then the section A of this part one is going to be dealing with distance versus time. Just the distance versus time, and then we'll deal with um, velocity versus time, and then acceleration versus time. And within this section, distance versus time, we can have several conditions. Okay, so we will not be doing all of them at the same time. We're going to have several conditions. This particular condition would include type of graphs are going to be distance versus time. The type of line, it would be all straight lines, no curves, and the direction of the lines will be in the positive direction. If you do understand reading of graphs, this information will be quite familiar to you. If you're not as familiar with graphs, then you will understand it in a very little while. The way I've decided to do it is to have a listing of the things that you usually see on a graph, or you usually have to use to interpret what a graph is actually saying. So I've decided to divide it into a description, then the action, and you have the distance, the velocity, the acceleration, the signs, positive or negative. Then we have the slope, the relationship, and the equation. As I move along, I could make some modification in those aspects that I've decided to highlight as as it becomes necessary. Okay, so let's start. Let's look at the graph. So this is the distance or location. Oh, and that's another thing. In some graphs, you would not see distance; you will see location, but they are the same thing. Um, so here we have the y-axis. This is the y-axis, and this is the x-axis. And on the y-axis, we have the distance representing distance, and we have the x-axis representing the time. All right, all of this is in the positive direction. Later on, we'll talk about when the graphs are here and this sort of thing. Those are not going to be positive. All right, so the line. This is the line that we're going to be looking at, and this is called a straight line. And we're gonna describe it. Okay, so in the description, and we're talking about the movement of an object. In other words, an object is actually moving, and that object could be a ball, it could be a car, it could be a train, it could be a plane, or whatever object is moving. And the assumption is that the object is moving from away from you, the viewer, whoever is the viewer. You're moving away from the object, and incidentally, that's what makes it positive, as you move away from the object. And that's different from if the object is coming toward you. In other words, if the object starts at a distance, at some distance which is not zero, and they move toward you, then that would be considered a negative movement. So in this case, in the first scenario, we're talking about positive differences, positive distances. Okay. All right. So let's look at the description. Object starts from distance 0, position 0, and constantly changes its distance with respect to time. Now, when an object changes its distance constantly with respect to time, that means that that object has a velocity that is constantly changing. Um, so the object's velocity the object's velocity remains the same throughout the time. So that's why we have a constant velocity, and that is represented by the straight line, constant velocity. Okay, we will see later what happens when the velocity actually changes, when the velocity is not constant. The distance the object is moving away from the point of origin, right? Moving away from the point of origin in this direction. Well, in the right direction, this direction, but it's represented by the y-axis on this graph. Alright, velocity is constant, and it is the same throughout. It does not change. The rate does not change. Okay, and because of that, the acceleration is constant, is zero, because the velocity is constant. The acceleration is zero. At some point, we're going to compare this distance versus time graph with an acceleration versus time graph. So we'll see how this straight line looks on an acceleration curve, on an acceleration graph. All right, so the signs, the distance is positive. This is a scalar quantity, the vector. By scalar and vector, we actually referring to the fact that if it's a vector, it could have a positive or negative. If it's a scalar, it could only have positive. We don't refer to it as positive, but in this case, it's either going to the right or to the left. Displacement, on the other hand, is a vector quantity, and that also could be positive or negative. But technically, distance is not really negative. We will say that it's going in the opposite direction, which is what we'll call negative. But all right, the slope is the velocity. The slope is the velocity, and the slope is in this case it's positive. The slope is positive because it's going in that direction. Now it's neither high nor low. It's right in the middle, and you will see how that makes sense in a bit. It's right in the middle there. Okay. Low would be here, high would be this way. There is a direct proportional relationship between the distance and time. And in previous videos, when we spoke about relationship, for that to happen, this line has to go through the 0 point, the point of origin, and also it has to be straight. And of course, in this case, the line is straight. The equation of the line is y is equal to k times x, and of course, the equation would also be x is equal to k, which is the constant, times y. All right. So either one of those equations would be correct. All right. In this instance, everything is basically the same. Everything is basically the same, and so I would not go over all of these things. The only change that we have in this example is that the velocity. See, the velocity is increasing very, very fast, very, very fast with respect to time. Okay. So the slope is going to be high, steep. Right, a steep slope means that the velocity is increasing very fast, right? So in this particular scenario, the only difference from this to the one before is that the velocity is changing very fast with respect to time, and the slope is going to be very high, which means that the object is moving very, very fast. Now this one is just the opposite now. Again, everything is the same. Everything is the same. It's just that in this case, the object is moving slow with respect to time, and therefore the velocity, the changing the velocity is pretty low. But remember, please remember, if you look at the acceleration, it is still zero, right? The acceleration is still zero because the velocity is constant. Because the velocity is constant. Down here, we could also put x is equal to k times y. All right. Now in this one, things are quite different. Things are not exactly the same as the one before. Several things have changed now. Let's see. The object is not moving. The object starts at some distance from the origin. Notice that this is the origin. The object did not start from the origin. At some distance, well, you had to start from the origin, but the reading here is not starting from the origin. The reading is not starting from zero, right? The reading is object starts from actually no. Object did not start from zero. That's correct. Object did not start from zero. Oh. So the object did not start from zero, and it did not change its distance with respect to time, and did not change the distance with respect to time. Okay, did not change its distance with respect to time. Now let me explain that. Well, that's is very little to explain. The object is not moving. All right, the object is not moving. The object started at some distance and it continued that distance. Again, the object started at this distance and continued with that same distance over time. All right. So again, the object did not start from zero, because if the object starts from zero, then it would have been here. Object started at some point that is not zero and continued in that positive direction, but it did not move. What does it say? The object is stay there. The object is stay there, and time is passing, but the object just stayed right there. All right. So if the object is not moving, then the velocity is going to be zero. If the velocity is zero, then the acceleration is going to be zero. Let me see. There's no relationship between the velocity and time because the object is not moving, right? Because the object is not moving. Well, it is a straight line. It is a straight line. Yes, it's a straight line, but the straight line did not come through the origin, right? It did not come through the origin. So that disqualifies it from being disqualifies it from having um, a direct relationship between, right? So let's put no direct. You don't have to put the word direct, but just to make sure that it's fully understood. All right. And again, the equation of line remains the same, but it would be zero because y in this case would be zero, right? Well, it would be the equation means nothing because y is zero. Well, y is not really zero, but y stops. The change in y would be zero, right? It's really the change in y would be zero. Okay. Let me see if I can find the insert symbol. Here we go. The change in y. There we go. That's it. It's the change in y. In other words, y here was, let's say, 10, and the y here is still 10. So there is no difference between this y and this y, and therefore the change in y would have been different. No. Change in x is something. You know, the distance in the x-axis would have been different. So that would not be zero. But of course, when you divide them, it is still going to come out. Okay. So this is an introduction to the the time versus distance, right? Or distance versus time video. I will continue on some of these videos, and I will continue to make some adjustments. But I personally I like this way of putting all these things in one package. Right? So until the next one, I will just continue with this. Okay. This is Nick. Bye.